The story of nature versus nurture begins long before the words themselves were used. It starts with people who tried to answer why a child behaves a certain way or why a plant grows tall in one place and short in another. The earliest recorded thoughts come from ancient Greece. Aristotle, the famous teacher of Alexander, wrote that every living thing has a purpose and a built-in pattern. He called this pattern form. In his work on biology, he said that the shape of a leaf or the strength of a muscle comes from the way the thing is made inside the body. He also noted that the environment can change how a thing grows. He wrote, "The shape of a tree is given by its nature, but the wind can bend its branches." This simple line shows that even then people saw both inner design and outside influence at work. Centuries later, a different voice entered the conversation. John Locke, a thinker from England, wrote about the mind as a blank slate. He called this tabula rasa, which means a clean board. In his book on human understanding, he argued that the mind starts empty, and that experience writes on it. He wrote, "No ideas are in us at birth. All come from sensation and reflection." Locke's idea was that everything we become is the result of what we see, hear, and feel. He did not deny that people are born with some basic abilities, but he put most of the weight on learning and experience. These two ideas, Aristotle's view of built-in patterns and Locke's view of a blank slate, set the stage for a debate that still runs today. The question can be put simply: are we mainly shaped by the parts we inherit, or by the places we live and the things we do? The answer is not simple, and that is why philosophers, scientists, and teachers keep talking about it. A first everyday example helps to see the clash. Imagine a pair of twins who go to the same school. They share many genes, so they look alike and have similar strengths. Yet one twin may love math and feel comfortable speaking in class, while the other may feel shy and avoid the same subjects. The school environment is the same for both, but the twins react in different ways. This shows that even with similar nature, the inner feelings and choices can differ, pointing to the role of nurture. A second simple example comes from gardening. Take two identical seedlings of the same flower. Plant one in a sunny spot and the other in a shady corner. After a few weeks, the sunny plant grows tall with bright blossoms, while the shaded plant stays short and its flowers are paler. The seed's genetic code is the same, but the light it receives changes how it looks. This picture of a plant shows how the outside world can shape the expression of inner design. Both examples are easy to see, yet they hide deeper arguments. One argument says that genes act like a script that tells the body what to do. Supporters of this view point to studies of twins who share the same DNA. They claim that if the script is strong, twins will act alike no matter where they grow up. A classic study from the 1800s looked at twins who were separated at birth and raised by different families. Researchers followed their lives and found that many of their interests, habits, and even health problems were similar. This seemed to prove that the script written in the DNA can set a fixed path. A second argument pushes the opposite side. It says that the environment writes the story, and that genes are only a starting point. Proponents point to cases where children from the same family grow up to have very different careers, habits, or values. They also note that if a child is raised in a supportive, rich environment, they often succeed, even if their parents had few resources. This view claims that the script can be rewritten by the world around us. Both arguments have strong points, but each also faces counter-arguments. The first counter-argument attacks the idea that genes fix everything. It says that even identical twins can develop different personalities because of the unique experiences each one has. For instance, one twin might have a teacher who encourages reading, while the other does not. Over time, those different experiences can lead to very different outcomes, showing that the script is not set in stone. The second counterargument challenges the claim that environment alone decides everything. It points out that some conditions, like a rare genetic disease, appear regardless of how loving or rich a family is. Even with the best care, a child with that disease will face certain limits. This suggests that there are parts of the script that cannot be changed by any environment. These back and forth debates are not just academic. They affect how societies design schools, healthcare, and laws. If nature is seen as dominant, then policies might focus on early medical testing and genetic counseling. If nurture is seen as dominant, then resources might go toward improving schools, neighborhoods, and parenting programs. The balance that is chosen can shape the lives of many people. Modern science adds new layers to the story. Genetics, the study of DNA, has grown into a powerful tool. Researchers can now read the exact code that makes a plant grow tall or a person have a certain risk for disease. At the same time, the study of culture looks at how shared beliefs, language, and customs guide behavior. Later sections of this video will explore how genes and culture interact, showing that the old nature-nurture split is becoming a more blended picture. A historical anecdote from the late 19th century helps illustrate the power of the twin study. In 1875, a German physician named Franz Kollmann began to collect data on twins who were raised apart. He traveled to many towns, asking families about the lives of twins who had been placed with different relatives. He found that many twins, even when raised in different languages, still showed similar temperaments. Kollmann's work laid the groundwork for later, larger studies that would use statistics to compare twins worldwide. His early notes read, "Even when the wind blows from different directions, the tree keeps its shape." This line captures the idea that some inner pattern stays the same despite different surroundings. Another anecdote comes from the world of agriculture. In the early 1900s, a botanist named Hugo de Vries set up garden plots in the Netherlands to test how light and soil affected plant growth. He planted the same species of wheat in two fields, one with rich, dark soil and plenty of sunshine, and another with poorer soil and less light. After a season, the wheat in the sunny field was taller, produced more grain, and looked healthier. De Vries wrote in his journal, "The seed carries the promise, but the earth decides the outcome." His simple experiment showed that the same genetic material could lead to very different results depending on the environment. Both anecdotes show that the debate has been alive for a long time. They also show how scientists use everyday observations to ask big questions. The twin study looks at human lives, while the garden experiment looks at plants, yet both speak to the same core idea. How much of what we see comes from inside, and how much from outside? To bring the ideas even closer to daily life, consider a modern analogy. Think of a computer program that runs on different computers. The code inside the program is like the genetic script. It tells the computer what to do. The computer's hardware, the speed of its processor, and the quality of its screen are like the environment. If the program runs on a fast computer, it works smoothly and quickly. If it runs on an old, slow computer, it may lag or crash. The same code can behave very differently depending on the machine it runs on. This picture helps to see why both nature and nurture matter. Another analogy uses music. A song has a melody written on paper, that is the nature part. When a band plays the song, the instruments, the room's acoustics, and the audience reaction shape how the music sounds. The same melody can become a soft ballad in a small hall or a loud rock anthem in a stadium. The written notes set a base, but the performance changes the experience. This shows how inner design and outer conditions work together. The debate also appears in everyday decisions. A parent might wonder whether a child's talent for drawing comes from the parent's artistic genes or from the art classes the child attends. A teacher may ask if a student's success in math is due to natural ability or to the extra tutoring the student receives. In both cases, the answer is rarely a single word. The truth is that many factors mix together. Later in the video, the discussion will move to how modern genetics can measure the influence of DNA. Scientists now use something called heritability to estimate what portion of a trait comes from genes. They also study epigenetics, which looks at how the environment can change the way genes work without changing the DNA itself. These ideas show that the old picture of a fixed script is becoming more flexible. At the same time, cultural studies will show how shared stories, values, and practices shape behavior across whole societies. The two fields will be linked, showing that nature and nurture are not separate islands, but parts of a larger ecosystem. One famous quote from Aristotle captures the early spirit of the debate. He said, "Nature does nothing in vain." This line suggests that every feature has a purpose built into it. Yet he also noted, the same thing can be altered by circumstance. Together, the two sentences hint at a balance between inner design and outer influence. John Locke offered a succinct line that still rings true. He wrote, "All ideas come from experience." This statement puts the power of the environment front and center. Yet Locke also believed that the mind has some basic powers that allow it to understand the world, showing that he did not think experience was the only factor. The two everyday examples introduced earlier can be revisited with the new ideas. The twins in school may share many genes, but the one who enjoys math might have had a teacher who praised his answers, while the other may have faced a teacher who focused on reading. The plant in the sun may have a gene that allows it to use light efficiently, but the lack of light in the shade prevents that gene from being expressed fully. In both cases, the inner code and the outer world join to shape the outcome. The counterarguments also find new support in recent research. Studies on twins raised together and apart have shown that many traits, like height, have a high genetic component, while others, like language accent, are more shaped by environment. This shows that the balance can shift depending on what is being measured. The claim that genetics set a fixed path is weakened when researchers find that even strong genetic influences can be altered by diet, stress, or education. Conversely, the claim that environment alone shapes everything is softened when a child with a genetic disorder still faces challenges despite a loving home. In the garden experiments of the early 20th century, scientists later discovered that the same wheat variety could be bred to tolerate less sunlight. By selecting plants that grew well in shade, they changed the genetic makeup of the crop. This shows that environment can push people to change the genetic code over generations, a process called natural selection. The story of how farmers saved crops from disease by choosing the strongest plants ties the two sides together. The environment chose which genes survived, and the genes gave the plants their ability to survive. A modern example of this blend appears in education technology. Some schools use computer programs that adapt to each student's learning speed. The program's code, nature, sets the range of possible lessons, while the student's answers, nurture, decide which path is taken. Researchers have found that students who receive personalized feedback improve faster than those who receive the same lesson, regardless of performance. This shows that a fixed design can work better when it interacts with the environment. Another modern story involves health. People with a family history of heart disease can lower their risk by exercising and eating well. The genes give a higher chance of problems, but lifestyle choices can reduce the impact. Doctors now tell patients that both their DNA and their daily habits matter. This practical advice reflects the long debate, now turned into everyday guidance. The philosophical roots of the nature-nurture question also appear in literature. In the novel The Brothers Karamazov, one character says, "Man is a mixture of his blood and his upbringing." This line, though not a formal philosophy, echoes the same tension that Aristotle and Locke felt. It shows that the idea has seeped into culture, not just academic circles. In sum, the early ideas of Aristotle and Locke set the stage for a debate that has travelled through centuries across labs, classrooms, and farms. The twin studies of the 1800s and the garden plots of the early 1900s gave concrete evidence that both inner design and outer conditions matter. Everyday examples of twins in school and plants in light make the abstract ideas clear. Counterarguments on both sides keep the discussion lively, and DNA is often described as a set of instructions for building a living thing. Think of a recipe book that tells a baker how to mix flour, sugar, and eggs to make a cake. In the same way, DNA tells cells how to make proteins, how to grow tissues, and how to respond to signals. The book is written in a language of 4 letters, A, T, C, and G, that pair up to form long strings called genes. Each gene is a small recipe that can be copied and used many times. The story of how scientists learned to read this book begins in a quiet garden in the 1860s. Gregor Mendel, a monk who loved peas, planted rows of pea plants with different colors and shapes. He kept careful notes on which traits appeared in the children of each plant. Mendel wrote, "The factors which determine the characters are transmitted from the parents to the offspring in a regular manner." His work showed that traits do not blend together but follow simple patterns of inheritance. Mendel's peas became the first proof that something invisible could control visible features. A century later, the mystery deepened. In 1953, James Watson and Francis Crick announced that DNA is shaped like a twisted ladder, a double helix. Their paper began, "We have discovered the structure of DNA." The discovery gave a picture of how the recipe book could be copied. When a cell divides, the 2 strands of the ladder separate, and each side serves as a template for a new partner. This copying process makes it possible for the same instructions to be passed from one generation to the next. These 2 discoveries, Mendel's patterns and the double helix, form the backbone of modern genetics. They show that the body and mind are shaped by a mixture of inherited codes and the environment. The nature versus nurture debate asks how much of a person's traits come from the DNA code and how much comes from life experience. One clear example of a genetic pattern is eye color. The classic story says that brown eyes dominate over blue eyes. If one parent carries a gene for brown eyes and the other carries a gene for blue eyes, the child is most likely to have brown eyes. The gene for brown pigment is strong, and it can mask the weaker blue gene. Yet the story is not absolute. Some families have children with green or hazel eyes, showing that more than one gene can affect the final shade. The eye color example shows how a simple instruction can guide a visible trait, but also how other factors can tweak the result. A second example is handedness. About 10% of people write with their left hand. Studies have found that left-handedness runs in families more often than chance would predict. A gene or set of genes may increase the likelihood of using the left hand. However, many left-handed people have no close relatives who are left-handed. This shows that the genetic influence is real but not decisive. The brain can adapt, and cultural pressure can also shape which hand a child uses. These examples lead to 2 common arguments. The first argument says that DNA is destiny. If the code is fixed, then a person's abilities, personality, and health are set at birth. Proponents point to conditions such as cystic fibrosis or Huntington's disease, where a single faulty gene almost always produces the disease. They quote Watson, "René is the master of all living things." This view treats the genome as a master plan that leaves little room for change. The second argument pushes back against determinism. It says that genes are only a small part of the story. Environmental factors such as nutrition, education, stress, and social support can alter how genes are expressed. The field of epigenetics studies how chemical tags can turn genes on or off without changing the DNA sequence. A famous study on twins raised apart showed that even with identical DNA, the twins developed different habits, tastes, and even accents. This evidence supports the idea that the environment can rewrite parts of the instruction book. Real-world applications of this knowledge are everywhere. Doctors use genetic testing to predict a child's risk for certain diseases. Parents may learn that a family history of heart disease increases their own risk and choose a healthier lifestyle. In education, teachers recognize that some students may have a genetic predisposition for dyslexia, and they can provide extra reading support early on. In sports, coaches may notice that certain athletes have a genetic makeup that favors fast-twitch muscle fibers, which help with sprinting. These uses show that understanding DNA can help shape better choices for health, learning, and performance. Modern interpretations blend the old ideas with new tools. The Human Genome Project, completed in 2003, mapped most of the human DNA code. It revealed that the genome contains about 20,000 genes, far fewer than once thought. Yet each gene can be used in many ways, and the interactions among them are complex. Researchers now talk about polygenic risk scores, which add up the tiny effects of many genes to estimate a person's chance of developing conditions like diabetes or schizophrenia. This approach moves away from the simple one gene, one trait view, and toward a picture where many small instructions work together. Another modern view comes from developmental neuroscience. The later section on brain development will explain how neurons grow, connect, and prune based on both genetic signals and experiences. For example, a child who learns to play the piano will see certain brain pathways strengthen, even though the underlying DNA that built those pathways remains the same. This shows that the same set of instructions can lead to many different outcomes, depending on what the child does. Analogies help keep the ideas clear. Imagine a house built from a set of blueprints. The blueprints tell where the walls go, where the doors are, and how big each room should be. However, the interior design, the paint colors, the furniture, the decorations, can change each time the house is lived in. The blueprints are like DNA, giving the basic shape. The interior design is like the environment, shaping the final experience. Both are needed for the house to feel like a home. A second analogy compares DNA to a computer program. The program contains code that tells the computer what to do. When the program runs, it can produce different results depending on the input it receives. If a user types in different commands, the output changes even though the program itself does not. In the same way, DNA provides the code, but the signals from the body and the world act as inputs that guide the final result. Historical anecdotes add color to the story. When Mendel first shared his P results with the scientific community, most people ignored him. It took decades before his work was rediscovered by scientists like Hugo de Vries and Carl Correns. This delay shows how a simple garden experiment can be missed when the larger scientific culture is not ready to listen. Another anecdote concerns Rosalind Franklin, whose X-ray photographs of DNA were crucial for Watson and Crick's model. Franklin's work was not fully recognized at the time, but later historians have praised her contribution as essential to understanding the double helix. Quotes from primary sources give a voice to the thinkers. Mendel wrote in his paper, "The factors are transmitted from the parent plants to the offspring in a regular manner." Watson and Crick declared, "We have discovered the structure of DNA." These short sentences capture the excitement of each breakthrough. The discussion of genetics also touches on ethical questions. If a test can tell a future risk for a disease, should parents use that information to make decisions about pregnancy? Should schools adjust teaching methods based on a child's genetic profile? These questions remind viewers that science does not exist in a vacuum. It lives within a society that must decide how to use new knowledge responsibly. In summary, DNA acts like a recipe book that tells cells how to build a body and a mind. Mendel's peas showed that traits follow predictable patterns, and Watson and Crick's double helix explained how the instructions are copied. Eye color and handedness illustrate how genes can guide visible traits, while twin studies and epigenetics show that the environment can change how those instructions are read. Modern tools such as genome sequencing and polygenic scores expand the view from single gene stories to complex networks. Analogies of blueprints and computer programs help keep the ideas clear, and historical anecdotes about peas and X-rays bring the science to life. The later section on brain development will show how the same genetic code works together with experience to shape the wiring of the mind. All of these points together paint a picture of nature and nurture as partners, not opponents, in the story of who we become. The brain grows much like a house that is built brick by brick. Each brick represents a group of cells that link together to form a circuit. The first bricks are laid when a child is born, but the builder does not finish the house in a single day. The builder adds new bricks, moves some bricks, and sometimes replaces old bricks with stronger ones. In the same way, neurons are born, grow, and form connections called synapses. Those connections become stronger when they are used, and they become weaker when they are not used. The process of adding, moving, and reshaping bricks is what scientists call brain development. Jean Piaget described this process as a series of stages. He wrote, "The child is not a little adult." Piaget meant that a child's mind works in a different way at each stage, just as a house under construction looks different at each floor. In the sensoromotor stage, which lasts from birth to about 2 years, the brain builds the foundations. Babies learn that shaking a rattle makes a sound, and that action creates a new connection in the brain. In the preoperational stage, which follows, the brain adds rooms for language and imagination. Children begin to use words, to pretend, and to sort objects by color or shape. Each new skill is like adding a new wall or window to the house. Lev Vygotsky offered a different view of how the bricks are placed. He believed that the social world acts like a set of scaffolds that help the builder reach higher levels. Vygotsky said, "What a child can do with help, he can do alone later." In a classroom, a teacher may show a child how to solve a puzzle. The child watches, copies, and then practices the steps on his own. The help from the teacher is like a temporary ladder that lets the child place a brick that would be too high to reach alone. Over time, the ladder is removed, but the brick stays, making the house stronger. Everyday life shows how the brick-by-brick process works. One clear example is how toddlers learn language. When a baby hears the word ball, ball, while a round object is shown, a tiny pattern of activity lights up in the brain. The next time the child hears ball, the same pattern is activated, and the connection grows a little stronger. As the child hears the word in many different settings, during play, in a story, in a song, the brain adds more bricks to the language room. By the time the child is 3, the word ball, ball can be called out without thinking, because the network of bricks is now well connected. A second everyday example is how a teenager reacts to stress. When a teen faces a difficult exam, the brain's stress system releases chemicals that make the body ready to act. The teen may feel a rapid heartbeat, sweaty palms, and a racing mind. If the teen has practiced coping skills, such as deep breathing or talking to a friend, the brain can quickly shift the pattern of activity from stress to calm. Those coping skills are like extra windows that let fresh air into the house, preventing the rooms from becoming too hot. If the teen has never practiced coping, the stress pattern may stay active longer, and the teen may feel overwhelmed. In both cases, the brain is still building and reshaping bricks based on what the teen has experienced. There are strong arguments that the brain's wiring is set at birth. Some researchers point to the fact that newborns already show preferences for faces, for human voices, and for certain patterns. They argue that these preferences are hardwired, like a blueprint that tells the builder where to place the first bricks. The nativist view says that genes provide a detailed plan for the brain, and that experience merely fills in the details. This view is often linked to the idea that certain abilities, such as recognizing a mother's voice, do not need teaching. Opposing that view, many scientists argue that experience reshapes connections throughout life. The concept of neuroplasticity means that the brain can change its wiring in response to what it does. For example, studies of musicians show that the part of the brain that controls finger movements grows larger with practice. The same principle applies to language learning, to stress coping, and to many other skills. The plasticity view says that the brain is a flexible builder that can add, remove, or remodel bricks at any age, as long as the right experiences are present. Both sides have evidence that supports them. The hardwired side points to twin studies that show high similarity in certain abilities even when twins are raised apart. The plasticity side points to cases where people recover from brain injury and learn new ways to do things they once could not. The truth likely lies somewhere in the middle. Genes may lay down the initial blueprint, but the environment adds the finishing touches. History provides vivid stories that illustrate how the brick analogy works. One famous case is that of Phineas Gage, a railroad worker who survived a severe brain injury in 1848. A metal rod pierced his skull, destroying much of the left frontal lobe. After the accident, Gage's personality changed dramatically. He went from being calm and reliable to being impulsive and rude. Doctors at the time wrote, "The case of Phineas Gage shows that the frontal part of the brain is involved in controlling behavior." Gage's story taught early scientists that specific brain areas are linked to specific functions, and that damage to those areas can change the way the house is built. Another early study comes from the work of Paul Broca in the 1860s. Broca examined a patient known only as Tan because he could only say the syllable Tan. After Tan's death, Broca found a lesion in the left side of the brain, in an area now called Broca's area. He wrote, "The loss of speech in this patient is due to a lesion in this specific region." This finding suggested that language has a dedicated part of the brain, like a special room in the house built for speech. Later researchers discovered that other language functions reside in different rooms, showing that the house has many specialized areas. These historical anecdotes link back to the genetics section that came earlier in the series. The genetics section explained how DNA provides the basic plan for the brain's layout, much like an architect's drawing. The brain development section now shows how those plans are turned into a real house, brick by brick, with the help of experience. The next part of the series will move from the bricks of the brain to the walls of culture. Culture adds meaning to the rooms, decides how the house is decorated, and influences how people move through it. The transition will show how the same brain can build different houses depending on the cultural tools it receives. To see the brick process in action, consider a child who learns 2 languages at the same time. The child hears Spanish words at home and English words at school. Each language creates its own set of connections in the brain. Over time, the brain builds 2 parallel language rooms that share some walls but also have separate doors. The child can switch between languages as needed, showing that the brain can handle multiple sets of bricks without confusion. This example shows how experience can shape the brain in complex ways, even when the genetic blueprint is the same for all children. A second example comes from a teen who joins a sports team. The teen learns the rules of the game, the positions of teammates, and the strategies for winning. The brain builds a network of bricks that help the teen anticipate moves, react quickly, and stay calm under pressure. When the teen faces a stressful exam, the skills learned on the field, such as focusing on the present moment and breathing steadily, can be used to manage stress. This cross-transfer of skills shows how the brain's architecture can be repurposed, much like a room that was first a bedroom and later becomes a study. The debate over nature versus nurture often turns into a tug-of-war between two extreme positions. One extreme says that the brain's wiring is fixed at birth, like a house built from a single set of bricks that cannot be changed. The other extreme says that experience alone can rewrite the entire house, no matter what the original blueprint looked like. Both extremes miss the fact that the brain is built from a mix of preset plans and ongoing construction. Genes give the builder a set of tools and a basic layout, while experience provides the materials and the instructions for each new floor. A key quote from Piaget helps keep the balance in view. He wrote, "Intelligence is what you use when you don't know what to do." This line reminds that the brain's ability to solve new problems comes from both the built-in structures and the learned strategies. Vygotsky added, "Through others, we become ourselves." This statement points to the role of social experience in shaping the brain's final shape. Modern interpretations of the brick analogy use brain imaging tools that can watch the building process in real time. Functional MRI scans show which areas light up when a child hears a new word. Diffusion tensor imaging tracks how the connections between brain regions grow stronger with practice. Researchers now see the brain as a dynamic construction site, where bricks are constantly added, removed, or reinforced. This view supports the plasticity side of the debate, while still acknowledging that some bricks are placed early because of genetic instructions. The story of Phineas Gage also shows that the brain can adapt after damage. After his injury, Gage learned new ways to behave even though his original frontal lobes were damaged. He found new strategies for planning and for controlling impulses, suggesting that other parts of the brain can take over some of the lost functions. This ability to rewire after injury is a powerful example of how experience can reshape the house, even when part of the original structure is gone. Early brain injury studies also include the case of patient HM, who had parts of his hippocampus removed to treat severe epilepsy. After the surgery, HM could not form new memories. Researchers wrote, "The loss of the ability to form new memories after removal of the hippocampus shows that this region is essential for memory." The case taught that some brain areas are critical for specific functions, but it also showed that other types of memory, such as skills, remained intact. This split suggests that different rooms of the house have different roles, and that some rooms can still work even when others are damaged. The building brick analogy also helps explain why twins can be different. Identical twins share the same genetic blueprint, but their experiences differ. One twin may grow up in a city, the other in a rural area. Their brains will build different rooms based on those experiences. The city twin may develop a stronger network for navigating crowds, while the rural twin may have a richer network for reading natural signs. This variation illustrates how the same set of genes can lead to different outcomes, depending. The garden picture that many people use to talk about nurture shows a plot of earth, a few rows of soil, and a fence that keeps out the wind. In that picture, the soil is the environment that surrounds a child. It is everything that touches the child. The family meals, the school walls, the language spoken at home, the games played after school, the weather that falls on the playground, the songs that play on the radio, the friends who sit next to a child at lunch. The garden also has many kinds of soil. Some soil is rich and dark, full of nutrients that help a seed grow fast. Some soil is thin and rocky, making growth slower. The idea of nurture is that the kind of soil a child is planted in will shape how the child grows, just as a gardener knows that the same seed can become a tall plant in good soil and a short plant in poor soil. Uri Bronfenbrenner, a psychologist who built the famous ecological systems theory, looked at the garden from many angles. He said that a child lives inside a set of circles that all affect the child. The closest circle is the family, the next circle is the school, then the community, then the larger culture, and finally the whole world. He wrote, "Development is a process of mutual influence between the child and the environment. In other words, the child does not just sit there while the garden grows around it. The child also moves the soil, spreads seeds, and sometimes pulls weeds." Bronfenbrenner's view helps people see that the garden is not a single patch of earth, but a whole landscape that changes over time. Margaret Mead, an anthropologist who traveled to many islands in the Pacific, also saw the garden as a place where culture plants seeds. She wrote, "If we could see the world as a whole, we would see that culture is the soil that shapes the plant." Mead studied how children in different societies learn to talk, to play, and to behave. She found that the same human body could learn very different habits simply because the surrounding culture gave different tools. Her work shows that the garden can have very different colors of flowers depending on the people who tend it. One easy way to see nurture at work is to look at what a child eats. In families where the parents cook fresh vegetables, whole grains, and fish, children learn to enjoy those foods. They grow up with a taste for healthy meals and often keep that taste into adulthood. In families where fast food and sugary snacks are the main meals, children learn to prefer salty, sweet, and greasy foods. Their bodies also adjust to those foods, and they may find it harder to like a plain salad later on. The diet example shows how the family's habits, the kitchen smells, the grocery store trips, and the meals shared at the table all act like soil that shapes the child's preferences. A second everyday example is the way a child picks out clothes. When a group of friends starts wearing a certain style, say bright sneakers with high socks, other kids in the group often follow. They may copy the brand, the color, the way the shoes are tied. The peer group becomes a kind of garden path that leads each child toward a shared fashion. Even if a child's parents dress differently, the pressure from friends can push the child to adopt the group's look. In this case, the peer group is the soil that changes the child's outward expression. These examples are not just stories. They link to the science of brain development. Researchers have shown that the brain's wiring is very flexible in early years. When a child hears a language spoken at home, the brain builds pathways that help the child understand and speak that language. When the child sees certain foods being prepared, the brain learns the smells, textures, and tastes that become familiar. When the child watches friends dress a certain way, the brain learns the social cues that signal belonging. The brain's ability to change in response to the environment is called plasticity. Plasticity is the reason why the garden can shape a plant even after the seed has sprouted. Social learning theory also fits into this picture. The theory says that people learn by watching others and then copying what they see. Albert Bandura, a psychologist who studied how children learn from adults, showed that children who saw an adult act aggressively toward a doll were more likely to act aggressively themselves. The garden of the child's environment, filled with models of behavior, therefore directly influences how the child acts. The diet and fashion examples are small cases of this larger idea. Children watch, they imitate, they become part of the pattern. Not everyone agrees that nurture can change everything. One counterargument says that culture is just a mirror of biology. Proponents of this view argue that humans have built cultures that fit their biological needs. For example, they say that people in cold climates eat more meat because their bodies need more heat, and they dress in thick clothing because their bodies cannot keep warm otherwise. In this view, the garden does not shape the plant. The plant's needs shape the garden. A quote from a biologist who holds this view reads, "The patterns of culture follow the patterns of human biology, not the other way around." A second counter-argument claims that the environment cannot change innate abilities. Some thinkers say that certain skills, such as musical pitch or mathematical reasoning, are hardwired into the brain. They argue that no amount of practice or good soil can make a person who lacks these abilities suddenly become a virtuoso or a mathematician. A classic line from a philosopher who defended this idea is, "Nature gives the seed its shape. The gardener can only help it grow, not change its form." This view suggests that the garden has limits and that some parts of the plant are set from the start. History provides two stories that show how people have tested the power of the garden. The first is the Hawthorne studies, a series of experiments at a factory in Chicago in the 1920s and 1930s. Researchers changed the lighting, the work hours, and the break times to see how workers would react. They found that simply paying attention to the workers made them work harder, no matter what the physical changes were. The study showed that the social environment, being observed, feeling valued, could change behavior. The Hawthorne studies are often used as a reminder that the garden's atmosphere can be as important as the soil itself. The second historical anecdote looks at how language spread across continents. When the Romans conquered large parts of Europe, they brought Latin with them. Over centuries, Latin mixed with local languages, creating new tongues such as French, Spanish, and Italian. The spread of a language shows how a cultural seed can travel, take root in new soil, and grow in different ways. It also shows that the environment can shape a language. The local climate, the terrain, the foods, and the daily life of the people all left marks on the words they used. The story of language spread illustrates how nurture can transform even something as deep as speech. Modern thinkers have taken these old ideas and given them new shape. Some researchers now talk about gene-environment interaction. They say that genes set up a range of possibilities, and the environment decides which part of that range is used. For instance, a child may have a gene that makes them good at learning music, but if the child grows up in a home where no music is played, the talent may stay hidden. In this view, the garden and the seed work together. The garden can bring out the best of the seed, but it cannot create a brand new seed. Other modern scholars focus on cultural evolution. They compare cultural change to biological evolution, but they stress that ideas can spread much faster than genes. They point to the way fashion trends move from one city to another in weeks, while a new species might take thousands of years to spread. This view shows that the garden can be reshaped quickly by ideas that travel through media, travel, and the internet. Real-world applications of the nurture side of the equation are many. In education, teachers design classrooms that feel safe and supportive, knowing that a positive environment helps students learn better. In health, doctors advise families to create home environments that encourage exercise and healthy eating, because the surroundings can lower the risk of obesity. In law, policymakers look at how neighborhoods affect crime rates, and they try to improve lighting, parks, and community centers to lower crime. All of these actions treat the garden as something that can be tended to produce better outcomes. One analogy that helps to see this is to think of a child as a young tree. The tree's roots need water, nutrients, and space to grow. If the soil is dry, the roots will not spread far, and the tree will stay small. If the soil is rich, the roots will grow deep, and the tree can become tall. The tree also needs sunlight, which is like the attention and encouragement a child receives. Too much shade, and the tree will not make many leaves. Too much sun, and the leaves may burn. The gardener, who is the family, the school, and the community, can add compost, water, and prune branches. The gardener cannot change the tree's species, but can help the tree reach its full potential. Another analogy is a recipe. A chef has a set of ingredients: flour, water, eggs. The chef can mix them in many ways, adding spices, changing cooking time, or using a different oven. The ingredients are like the child's biology, and the recipe steps are like the environment. The same ingredients can make a cake, a bread, or a pastry depending on how they are treated. The chef cannot turn water into chocolate, just as the environment cannot give a child a brand new organ. But the chef can decide whether the final dish is sweet, salty, or sour. The environment decides many of the outcomes we see in people. Quotes from primary sources add weight to these ideas. Bronfenbrenner wrote in his book, The Ecology of Human Development, the child's development is a product of the interactions that occur in the multiple layers of his environment. Mead, in her classic work, Coming of Age in Samoa, observed, the child learns the ways of his people by being surrounded by them. The surroundings are the teachers. The Hawthorne researchers noted, when people feel observed, they tend to improve their performance, a line that still appears in many textbooks. A linguist who studied the spread of language, Edward Sapir, said, "Language is a living thing that grows in the soil of culture." Connecting back to earlier sections on brain development, the nurture side shows why early experiences matter. The brain's plasticity means that the garden's soil can shape the pathways that lead to language, math, and social skills. If the garden is rich in language, the child's brain will develop strong language circuits. If the garden lacks language, the circuits may stay weak. The same holds for social learning. The more the child watches others cooperate, the more the brain builds networks for empathy and cooperation. In the final view, nurture does not act alone. It works with nature, with the seed inside the soil. The garden can make a seed grow tall, short, straight, or twisted, but it cannot change the seed's species. The seed can also influence the garden by sending roots that pull nutrients, by dropping leaves that become new soil. The picture of a garden with many soils helps keep this balance clear. By tending to the garden, by providing good food, supportive friends, rich language, and safe places, society can help each child grow as well as possible. The story of nurture is a story of many small actions that add up. A parent who cooks a vegetable stew, a teacher who reads aloud every day, a friend who shares a new song, a community that builds a. The interactionist view holds that genes and environment are not opponents, but partners. It says that a person's traits are the result of a long dance between the biology that comes from the seed and the experiences that come from the sun. Think of a small seed that has the potential to become a tall oak. The seed carries the genetic plan for the tree's shape, leaf pattern, and bark. Yet without sunlight, water, and soil, the seed cannot grow. In the same way, a child is born with a set of genetic tendencies, but those tendencies need the right surroundings to become visible. This simple picture helps to see why many scientists now prefer the word interaction over the old debate that tried to put nature on one side and nurture on the other. Robert Plomin, a leading geneticist, often speaks about this balance. He writes, "Genes influence behavior, but they do not determine it." That short line captures the core of the interactionist stance. Plomin's work on twins shows that even when two people share almost the same DNA, their lives can still differ because of the places they live, the schools they attend, and the friends they keep. Jerome Kagan, a famous psychologist, adds another piece. He says, "The child is not a blank slate, but a mixture of innate tendencies and experience." Kagan's studies of shy children illustrate how a temperament that is partly built into the brain can be softened or strengthened by the way parents and teachers respond. One everyday example of this blend can be seen in a child who shows an early love for music. The child may have a genetic sensitivity to rhythm and pitch. That sensitivity is like the seed that carries the potential for musical skill. When the child receives piano lessons, encouragement from parents, and a chance to play with other kids, the environment supplies the sunlight. The lessons give structure, the encouragement gives confidence, and the group playing offers feedback. Over time, the child's skill grows far beyond what the genetic seed alone could have produced. The reverse can also happen. A child with a natural sense of rhythm, but no access to instruments or teachers, may never develop the same level of ability. The interactionist view explains why both the seed and the sunlight matter. A second everyday example involves a shy teenager who feels uncomfortable in social settings. Research shows that shyness has a modest genetic component. That means some teenagers start life with a brain that reacts more strongly to new people. If that teenager meets a group of supportive friends, the friends act like a warm sun that helps the seed sprout. The friends listen, invite the teen to join activities, and do not push too hard. Over weeks and months, the teen learns new ways to talk, to listen, and to feel safe. The teen's confidence grows, showing that the environment can change the expression of the genetic tendency. If the teen instead faced criticism or exclusion, the shy trait could become more fixed. The story of the shy teen shows how the two forces work together in daily life. The interactionist view is not without critics. One criticism says that the idea of interaction is too vague to be useful. Critics argue that if every outcome is explained by a mix of genes and environment, the theory loses predictive power. They ask for clearer rules that say when genes are stronger and when the environment wins. In response, interactionists point to studies that actually measure how much each side contributes in specific cases. For example, the Minnesota twin family study, started in the 1970s, followed twins who were raised together and twins who were raised apart. The study found that many traits, such as intelligence and personality, showed both a genetic influence and a clear environmental effect. The numbers from the study give a concrete way to see how the two forces add up, rather than leaving the idea as a vague label. A second counterargument claims that one factor always dominates. Some people say that either genes are the master or the environment is the ruler. They point to cases where a single gene seems to cause a disorder, or to cultures where education can lift anyone out of poverty. The interactionist reply is that most human traits are complex. Even a single gene can be turned on or off by the environment. In the case of a disorder like phenylketonuria, a genetic defect can be managed by a special diet, showing that the environment can stop a gene from causing harm. In the case of education, a supportive school can boost a child's learning, but the child's own curiosity and memory still matter. The interactionist view says that the balance shifts from case to case, but both sides always play a role. Historical anecdotes help to see how the view developed. The Minnesota twin family study, mentioned earlier, gave scientists a rare chance to separate the genetic and environmental parts. Twins who shared the same DNA but grew up in different homes still showed many similar traits. At the same time, differences in their lives, such as the schools they attended or the neighborhoods they lived in, explained the remaining variation. The study's lead researcher, Thomas Bouchard, wrote, "The similarity of twins raised apart tells us that genetics set the stage, but the play is written by experience." This quote captures the spirit of interactionism in a clear way. Another early piece of evidence came from adoption research in the 1950s. Researchers followed children who were placed in new families shortly after birth. They compared the children's traits to those of their biological parents and to those of their adoptive parents. The findings showed that language ability and certain personality traits resembled the biological parents, while attitudes towards school and health habits resembled the adoptive parents. This pattern showed that both the inherited blueprint and the daily life shape a person. The adoption studies gave a real-world picture of how nature and nurture meet. The interactionist view also ties back to earlier sections on genetics and culture. The genetics section explained how DNA carries instructions that affect brain development. The culture section described how shared beliefs, customs, and language shape thinking. Interactionism says that the two sections are not separate chapters, but parts of one story. A gene that makes a brain more sensitive to language can be amplified when a child grows up in a culture that talks a lot. Likewise, a cultural practice that values cooperation can bring out a genetic tendency to be empathetic. By linking the two sections, the video shows that the whole picture is richer than the sum of its parts. Modern interpretations of interactionism have taken the idea into new fields. In neuroscience, scientists now watch how the brain changes when a person learns a new skill. They see that learning creates new connections between neurons, a process called neuroplasticity. Neuroplasticity shows that the brain's wiring, which is partly set by genes, can be reshaped by experience. In education, teachers use the concept to design classrooms that respect each student's strengths while providing the right challenges. In mental health, therapists combine medication, which works on the brain's chemistry, with talk therapy, which changes patterns of thought. All of these practices reflect the belief that genes and environment are partners. A simple analogy can help to remember the idea. Imagine a recipe for a cake. The recipe lists the flour, sugar, eggs, and butter. These are like the genes. But the baker still needs a warm oven, the right amount of time, and the skill to mix the batter. The oven temperature and the baker's care are like the environment. If the oven is too cold, the cake will stay flat, no matter how good the ingredients are. If the batter is poorly mixed, the cake will be lumpy, even with perfect ingredients. The final cake depends on both the recipe and the baking process. This picture makes it easy to see why scientists now speak of interaction rather than competition. Quotes from primary sources give the view a personal voice. Plomin, in his book Blueprint, writes, "Or the genetic influence is not a destiny, but a probability." Kagan, in his article on temperament, says, "A child's early fear is a signal, not a sentence." These lines remind the listener that the science is about chances, not certainties. They also show that the leading thinkers see the two forces as working together. The interactionist view also helps to answer everyday questions. Why do some people become great athletes while others do not, even if they train hard? The answer is that a genetic makeup that favors fast muscle fibers gives a head start. But training, coaching, and nutrition are needed to turn that head start into success. Why do some students excel in math while others struggle, even with the same teacher? Some students may have a brain that processes numbers more easily, but a supportive classroom that offers practice and encouragement lets them reach their potential. In each case, the outcome is a mix of what the body brings and what the world offers. Critics who say interaction is too vague can look at the growing field of epigenetics. Epigenetics studies how the environment can turn genes on or off. For instance, a child who experiences chronic stress may have stress-related genes marked in a way that makes them more likely to feel anxious later. If the child later receives a calm, caring environment, those marks can be reduced. This research gives a concrete way to see how environment changes the expression of genes. It turns the vague idea of interaction into measurable changes in the body. The claim that one factor always dominates also meets evidence from studies of language acquisition. Babies are born with a brain that can detect speech sounds, a genetic readiness. Yet, if a child never hears language, that readiness will not become a spoken language. Conversely, A child who hears many languages will develop the ability to speak several, even if the genetic predisposition for each language is modest. Both sides matter, and the balance can shift depending on the situation. In the modern world, technology adds a new layer to the interaction. Social media provides a constant stream of information and feedback. A person's genetic tendency to seek social approval can be amplified by the likes and comments on a post. At the same time, a supportive online community can help a shy person practice speaking and gain confidence. The interactionist view says that new environments, like digital ones, still work together with the brain's wiring. The interactionist view does not claim that every detail can be predicted. It simply says that looking at genes alone or at environment alone gives an incomplete picture. By combining the two, a richer understanding emerges. This approach respects the complexity of human life and avoids the trap of saying that one side is the sole ruler. It also matches the evidence from many fields, from psychology to biology to education. To close, the interactionist view paints a picture of life as a garden. The seed holds the plan for a plant, but the gardener decides where to place it, how much water to give, and when to prune. The plant's growth depends on both the seed and the gardener's care. In human terms, the seed is the DNA, the gardener is the family, school, culture, and society. When the seed and the gardener work together, the result can be a strong, healthy tree. When one side is missing, the tree may stay small or become twisted. The story of nature and nurture is therefore a story of partnership, not opposition. By keeping the focus on both sides, the video invites the viewer to see themselves as both a product of biology and a maker of their own path. It encourages a view that respects the power of genetics while also honoring the influence of experience. In this calm, reflective tone, the narrator hopes that the audience will carry the idea of interaction into everyday life, seeing each choice, each relationship, and each learning moment as part of the ongoing dance between seed and sunlight. The story of nature versus nurture is filled with experiments that still echo in today's classrooms and labs. Each study adds a small piece to the puzzle of how much of a person is shaped by genes and how much by experience. In this part of the journey, the focus turns to the people who built the experiments, the ideas they tested, and the questions that still linger. One of the earliest voices in the debate was B.F. Skinner. He believed that behavior could be understood by looking at what comes after it. He called this the tool of effect. In simple terms, if something good follows an action, the action is likely to happen again. If something bad follows, the action will probably stop. Skinner built a box called the operant chamber. Inside, a hungry rat could press a lever. When the rat pressed the lever, a food pellet fell. The rat learned quickly that pressing the lever meant food. Skinner wrote, "Behavior is a function of its consequences." This short line captures his whole view. The experiment showed that a clear reward can shape a new habit. Skinner's work did not stay in the lab. Teachers began to use reward charts in classrooms. A child who finished a reading assignment might earn a star. 10 stars could be traded for extra playtime. The idea was the same as the rat's lever. A visible reward makes a behavior more likely. The system is easy to see, and it works for many children. It also shows how a simple environment can guide learning. Albert Bandura offered a different angle. He thought that people could learn just by watching others. He called this observational learning. To test it, Bandura set up a room with a small child and a larger adult model. The adult was asked to hit a Bobo doll with a hammer. The child watched. Later, the child was left alone with the same doll. Many children copied the adult's aggressive actions. Bandura wrote, "People can learn new behaviors by watching the actions of others." The experiment suggested that not only direct rewards, but also the actions of people around us can shape behavior. Bandura's findings fit neatly with the idea of a classroom reward system. A teacher who models calm problem-solving can help students learn to stay calm. The teacher's behavior becomes a live example, not just a written rule. In this way, the environment provides both direct rewards and role models. Harry Harlow took the question to the world of monkeys. In the 1950s, Harlow built two kinds of mother figures for baby rhesus monkeys. One was made of wire and gave the baby food. The other was soft cloth and gave no food. When the baby monkeys were hungry, they went to the wire mother to eat. But when they were scared, they clung to the cloth mother. Harlow wrote, "Love is the most powerful, most fundamental need of the infant." The simple setup showed that comfort and security can be more important than food. The experiment suggested that emotional needs are part of nurture, not just physical ones. Harlow's work also gave a vivid picture of how early experiences shape the brain. Later studies showed that monkeys raised with the cloth mother had better stress responses. Their brains grew in ways that helped them handle fear. This linked the idea of nurture to biology, a theme that will reappear later when brain and culture are discussed together. Another classic study is the marshmallow test. Walter Mischel placed a child in a room with a marshmallow. The child was told that if they waited 5 minutes without eating the treat, they could have a second marshmallow later. Some children ate right away. Others waited. Years later, the children who waited tended to have higher school grades and better health. The test showed that self-control can be learned. It also suggested that a small change in the environment, a simple promise, can have a big impact on later life. The marshmallow test ties back to Skinner's reward idea. The promise of a second marshmallow is a future reward. It also links to Bandura's model. Children who watched adults wait for a reward might learn to wait themselves. The experiment bridges the gap between simple lab tasks and real-life decisions. Even as these studies offered powerful evidence, they also sparked criticism. One major counterargument is that lab settings are too artificial. In a quiet room, a rat can press a lever without distractions. In a busy classroom, a child faces many sounds, friends, and emotions. Critics say that the clean conditions of a lab do not capture the messiness of everyday life. They argue that what works in a box may not work in a bustling school. A second counterargument focuses on generalizability. The marshmallow test used a small group of children from a specific city in the 1960s. The results may not apply to children from different cultures or economic backgrounds. Some researchers have repeated the test in other countries and found that many children eat the marshmallow quickly, not because they lack self-control, but because they do not trust that the promised second treat will really appear. This shows that cultural expectations can change how a simple experiment is understood. Historical anecdotes add depth to the discussion. The Stanford prison experiment, led by Philip Zimbardo in 1971, placed college students into a mock prison. Some were guards, others were prisoners. Within a few days, the guards began to act harshly, and the prisoners showed signs of stress. The experiment was stopped early because it became too intense. Zimbardo later said, "The situation created a powerful influence over behavior. The study highlighted how powerful a social setting can be in shaping actions, even when participants know they are only acting." The Harlow monkey studies also carry a human story. In one famous case, a baby monkey named Susan was raised with the cloth mother, but never learned to climb or explore. She stayed close to the soft figure, showing fear of the world beyond. The anecdote illustrates how a lack of challenge can limit development. It also warns that too much comfort can hinder learning. Harlow's work reminded scientists that nurture includes both safety and the chance to face small risks. These experiments are not just stories from the past. They still shape modern ideas about education and mental health. In many schools, teachers use token economies that echo Skinner's lever system. A student earns a token for good work, and later trades tokens for a prize. The system gives immediate feedback, helping students see the link between effort and reward. In therapy, Bandura's concept of modeling is used to help people change harmful habits. A therapist might demonstrate a calm way to handle anger, letting the client watch, and then try the same approach. The client learns by observation, not just by direct instruction. This shows how the idea of learning from others lives on. Neuroscience now adds a new layer. Brain imaging shows that when a child receives a reward, a part of the brain called the striatum lights up. When a child watches another person succeed, the same area can become active. This suggests that the brain treats direct rewards and observed rewards in similar ways. The finding bridges the old experiments with modern brain science, tying back to earlier sections on how the brain and culture interact. Culture also colors how these experiments are understood. In some societies, waiting for a reward is seen as a sign of respect. In others, immediate gratification is normal. When the marshmallow test is run in a culture where elders often keep promises, children may wait longer. The cultural lens shows that nurture is not just about the immediate environment, but also about shared beliefs and values. Real-world examples bring the ideas home. Imagine a soccer coach who praises a player for a good pass. The player feels good and tries the pass again. The coach's praise works like a reward, shaping the player's habit. In another case, a teenager watches an older sibling study late at night and get good grades. The teenager may start to study later, copying the behavior. Both examples echo the findings of Skinner and Bandura, showing that rewards and observation guide daily life. The debate also includes the idea that genetics set limits. Some researchers point to twin studies that show identical twins share many traits even when raised apart. This suggests that nature has a strong hand. Others argue that twins share many experiences, making it hard to separate nature from nurture. The conversation continues, with each new study adding nuance. One modern interpretation comes from epigenetics. This field looks at how the environment can turn genes on or off. For example, a child who grows up in a stressful home may have stress-related genes activated, affecting brain chemistry. If the child later moves to a supportive school, the new environment can help reverse some changes. Epigenetics shows that nature and nurture are not separate tracks, but intertwined threads that shape each other. Another modern view uses computational models. Researchers build computer simulations where virtual agents learn by reward or by watching others. The simulations can test many scenarios quickly. They often find that a mix of direct rewards and social learning leads to the most adaptable agents. This mirrors the mixed findings from the classic experiments. The story of the nature versus nurture debate is far from over. Each experiment, from Skinner's liver to Bandura's Bobo doll, from Harlow's cloth mother to the marshmallow test, adds a piece to the picture. The criticisms remind that no single study can answer all questions. The historical anecdotes remind that human behavior can shift dramatically when the setting changes. The modern work on brain imaging and epigenetics shows that the old ideas still have life in new science. When the viewer thinks about their own habits, the lesson is simple. A clear reward can shape a habit. Watching a role model can teach a skill. A safe, caring environment can help the brain grow. At the same time, the viewer should remember that experiments in quiet rooms may not capture the full story of a busy life. The viewer should also keep in mind that cultural expectations can change how a reward is seen. In the end, the debate is not about choosing nature or nurture, but about seeing how they work together. The brain provides the hardware, the genes set the basic design, and the environment writes the software. Culture offers the language that guides the code. The classic experiments show how small changes in the environment can steer behavior, while modern science shows how those changes can reshape the brain itself. The next part of the journey will look at how these ideas play out in the digital age. As screens become a new environment, new experiments will test how online rewards and virtual role models shape minds. The story continues, and each new study adds another chapter to the long conversation about what makes us who we are. The modern world now holds a tiny device that can read the code of life in a way that feels as simple as scanning a grocery item at a checkout lane. In that picture, a person places a bag of fruit on a scanner, the machine flashes a light, and a number pops up on the screen showing the price. In the same way, a DNA testing kit takes a small swab from the inside of a cheek, sends it to a lab, and the lab's machines flash light across the strands of DNA, turning the pattern of letters into a list of facts. The list may say where ancestors lived, whether a certain health risk is higher than average, or which traits are more likely to appear in future children. The analogy helps to keep the idea clear. Just as the scanner does not decide what a fruit is, the test does not decide a person's fate. The story of how that scanner was built began with a massive effort called the Human Genome Project. The project started in 1990 and brought together scientists from many countries. Their goal was to read every letter in the human genome, the complete set of DNA that makes up a human being. In 2003, the project announced that it had finished a reference map of the genome. The map was like a master key that opened many doors for research. One of the people who helped write that story was Craig Venter, a scientist who later built a private company to sequence genomes faster and cheaper. Venter once said, "We are the first species to read our own genome." That quote captures the awe that many felt when the first full picture of human DNA appeared on a screen. The work of the Human Genome Project turned a dream into a tool that can be bought at a pharmacy. Today, a person can order an ancestry kit online, receive a small tube, swab the inside of a cheek, and send the sample back. Within weeks, the kit returns a report that shows percentages of DNA that match regions such as Western Europe, East Asia, or Saharan Africa. The report may also point out a few genetic markers that suggest a higher chance of developing conditions like type 2 diabetes or lactose intolerance. In another everyday example, a health risk report may focus on a single gene called APO. If a person carries a certain version of APO, the report may say that the risk for late-onset Alzheimer's disease is higher than for someone without that version. The report does not say the person will get the disease, only that the risk is higher. These reports are often presented as clear answers. But there are two important counter-arguments that should be heard. The first is the idea that DNA reports are deterministic. Determinism is the belief that a single cause, such as a gene, fully decides an outcome. Some people read a health risk report and think, "If I have this gene, I will get the disease." That view ignores the many other factors that shape health, such as diet, exercise, stress, and environment. The second counter-argument is that DNA reports are often misinterpreted. The language used in a report can be technical, and the numbers can be confusing. For instance, a report might say a risk is 5 times higher than average. Without context, a person may think that means a 50% chance of getting the disease, when in fact the baseline risk might be only 2%, making the absolute risk about 3%. Misreading the numbers can cause unnecessary worry or false confidence. A look back at history shows how quickly the field moved from big labs to kitchen tables. In the late 1990s, The race to map the human genome was a headline story. Companies like Celera Genomics, led by Craig Venter, competed with the public project to finish the map faster. Celera used a new method called shotgun sequencing, which broke the genome into many tiny pieces and then reassembled them with computers. The competition pushed the timeline forward, and the reference genome was finished 2 years earlier than many expected. That race showed how a blend of public funding and private ambition could speed up science. Soon after the reference genome was released, a few companies began offering direct-to-consumer DNA tests. In the early 2000s, one of those companies, 23andMe, sent out kits that promised to reveal ancestry and health information. The company quickly ran into trouble when the U.S. Food and Drug Administration, FDA, warned that the health reports could not be sold without proper approval. The FDA's concern was that people might act on the information without a doctor's guidance, leading to harmful decisions. The company stopped offering health reports for a few years, then returned with a more regulated approach. This early scandal reminded everyone that the technology, while powerful, needs careful oversight. The modern scene of DNA testing is shaped by both the genetics and the interactionist sections of the larger philosophy of nature versus nurture. The genetics side emphasizes that the DNA code carries real information that can influence traits. The interactionist side stresses that genes do not act alone. They work together with the environment, lifestyle, and social factors. When a person looks at a DNA report, the report is a piece of the genetic side, but the person's life story adds the interactionist side. The two sides together create a fuller picture. One way to understand how the two sides meet is to think about a garden. The seeds in the garden are like the genes. They hold the potential for a certain kind of plant. The soil, water, sunlight, and gardener's care are like the environment and choices. A seed may be capable of growing a tall sunflower, but if the soil is poor or there is not enough water, the plant may stay short or not grow at all. In the same way, a person may have a gene that raises the risk for high blood pressure, but a healthy diet and regular exercise can keep the blood pressure low. The garden analogy keeps the idea simple and vivid. Another everyday analogy compares DNA testing to a weather forecast. A forecast looks at many data points: temperature, humidity, wind, to predict whether it will rain. The forecast does not guarantee rain, but it gives a probability that helps people decide whether to carry an umbrella. A DNA health report works similarly. It looks at genetic data to give a probability of a health outcome. Just as a forecast can be wrong if a sudden storm appears, a DNA report can be misleading if other factors change the risk. The analogy reminds listeners that probabilities are tools, not guarantees. The impact of DNA testing reaches beyond personal curiosity. In medicine, doctors sometimes use genetic information to choose a drug that works best for a patient. This practice is called pharmacogenomics. For example, a gene called CYP2C19 influences how the body processes a heart medication called clopidogrel. If a person has a version of the gene that slows down the drug's activation, the doctor may choose a different medication. This real-world use shows how DNA testing can guide treatment, not just tell a story about ancestors. In another field, law enforcement has used DNA to solve crimes. When a crime scene leaves a trace of DNA, investigators can compare it to a database of profiles. The technique helped catch the Golden State Killer after decades of cold cases. While this use is powerful, it also raises ethical questions about privacy and consent. The philosophy of nature versus nurture does not answer those questions directly, but it reminds us that the power of DNA data can affect many parts of life. Quotes from primary sources add depth to the discussion. In a 2001 interview, Francis Collins, the leader of the Human Genome Project, said, "The genome is a map that will guide us, but the road is still being built. The statement captures the idea that the genome provides directions, but the journey of understanding still continues. Another quote comes from a 2015 article by Venter, where he wrote, "Through the ability to read and write DNA will change the way we think about ourselves." This line points to the shift from seeing DNA as a static code to seeing it as a dynamic tool. The modern DNA testing market is also a story of economics. The price of a full genome sequence fell from about $100 a million in the early 2000s to less than $1 That drop made it possible for companies to sell kits for under $100. The cheaper price opened the market to millions of people, but it also created a flood of data that scientists are still learning how to store and interpret. The volume of data raises questions about who owns the information and how it can be used. One practical tip for anyone who receives a DNA report is to look for the confidence level that the lab provides. Many labs will say that a certain marker is high confidence or low confidence. High confidence means the test has been repeated many times and the result is reliable. Low confidence means the result might change with a better test. Understanding this helps avoid overreacting to a single number. Another tip is to combine the DNA information with family history. If a person's grandparents all lived to 90, that suggests a family pattern of longevity that may offset a small genetic risk for heart disease. Conversely, if many relatives have a certain condition, the DNA risk may be a clue that the family history is important. The interaction of family stories and genetic data is a classic example of the nature-nurture blend. When the first genome was published, scientists wrote in the paper, "The sequence of the human genome provides a foundation for a new era of biology." That optimism still guides the field. Yet the same paper also warned that the interpretation of the genome will require many years of research. The warning is a reminder that the science is still growing, and that the reports people get today are only a small part of a larger puzzle. The conversation about DNA testing also touches on the idea of identity. An ancestry report may tell a person that 30% of their DNA matches a region in South America. That fact can spark interest in learning about that culture, trying new foods, or traveling to a new country. At the same time, the report may not capture the full story of a person's life, language, or community. The report offers a piece of the picture, not the whole canvas. Critics of DNA testing sometimes argue that the focus on genetic explanations can reduce the importance of social factors. For example, a study might show that a certain gene is linked to lower academic performance. If schools start labeling students based on that gene, they may ignore the role of teaching quality, resources, or motivation. This criticism reflects the deterministic counterargument and underscores why the interactionist perspective is needed. In response, supporters point out that DNA testing can empower people. Knowing a predisposition to a condition can motivate lifestyle changes, such as exercising more or quitting smoking. Some people also use the information to plan for future medical care, such as getting regular screenings earlier. The empowerment view aligns with the idea that knowledge, when used wisely, can improve health outcomes. The future of DNA testing may include whole genome sequencing for everyone. Instead of testing a few markers, a full genome would give a complete picture of all genetic variations. Researchers are already working on ways to turn that massive amount of data into simple advice. One proposed method is to use artificial intelligence to read the genome and suggest personalized diet or exercise plans. While the idea sounds exciting, it also raises concerns about data security and the accuracy of algorithmic advice. A final anecdote comes from the story of a man named Jim, who bought an ancestry kit out of curiosity. The kit told him that he had a small percentage of DNA from a region in the Middle East. Intrigued, Jim traced his family tree and discovered a great-grandfather who had emigrated from that region in the early 1900s. The discovery gave Jim a new sense of connection to a culture he had never known. At the same time, the test also showed a small risk for a condition that his doctor explained could be managed with regular checkups. Jim's experience shows how a DNA report can blend personal history with practical health information, illustrating the mix of nature and nurture. In summary, modern DNA testing works like a scanner that reads a tiny code and turns it into useful numbers. The technology grew out of the Human Genome Project, a massive scientific effort that finished a reference map of human DNA. Figures such as Craig Venter helped speed up the process and bring the cost down. Everyday people now use kits that reveal ancestry and health risks. Two strong counter-arguments warn against seeing DNA as destiny and against misreading the numbers. Historical anecdotes about the race to map the genome and early testing scandals show how fast the field moved and why regulation matters. Real-world uses in medicine, law enforcement. The story of a child learning from a tablet is a small picture that can hold a whole world of ideas about how nature and nurture meet in the digital age. In the scene, a bright screen glows while small fingers swipe, tap, and scroll. The child watches a video about how a plant grows, then draws a picture of a tree on a digital canvas. The same child later opens a game where a team must solve a puzzle together. In each moment, the device does more than give information. It shapes the way the child thinks, feels, and acts. This is the heart of the new nurture landscape that social media and technology have created. The roots of this discussion go back to early debates about nature and nurture. In the old days, philosophers such as John Locke said that the mind starts as a blank slate, a tabula rasa, and that experience writes on it. Later, thinkers like Francis Galton argued that genes set the limits and that the environment can only fill in what is already there. The digital world adds a fresh layer to that old conversation. Now, the environment is not just books, playgrounds, or parents. It is a network of screens, apps, and endless streams of data that can reach a child at any time. One modern voice that helps to understand this shift is Sherry Turkle, a professor who studies how people relate to technology. In her book, Alone Together, she writes, "Technology does not just change what we do, it changes who we are." Turkle points out that when children grow up with tablets and social feeds, they learn to think about themselves in terms of likes, comments, and notifications. The child in the picture may see a badge on the screen after finishing a puzzle, and that badge becomes a small sign of success. Over time, such signs can shape a sense of self that is tied to digital approval. Another important thinker is Nicholas Carr, who wrote the essay, "Is Google Making Us Stupid?" Carr argues that the internet encourages quick scanning rather than deep reading. He says, "The net is a kind of external brain that stores and serves up information on demand, but it also rewires the way the brain works." In the context of a child using a tablet, Carr's idea suggests that the brain may become more accustomed to short bursts of information, which can affect attention spans and memory habits. These two thinkers set up the main arguments for the new nurture landscape. The first argument says that digital life expands the ways in which a child can learn. A tablet can show a video of a volcano erupting, then let the child build a model in a 3D app. Online games can require a child to plan, coordinate, and communicate with teammates across the globe. This teamwork can teach skills that were once only learned on a sports field or in a classroom. Social feeds can give a child a sense of belonging to a larger community, showing that many people share similar interests. The second argument focuses on how technology can change habits in a deeper way. When a child checks a phone every few minutes, a pattern of constant interruption can become the norm. The habit of waiting for a notification can shape how the child deals with boredom, stress, and even sleep. In this view, technology does not just add new tools, it rewrites the rhythm of daily life. Both arguments have strong support, but they also face counterarguments. One common counterargument says that technology only amplifies traits that already exist in the child. If a child is already shy, a social feed may give them a safe place to express themselves, but it does not make them outgoing. If a child already enjoys solving puzzles, a game will simply give them more puzzles. In this view, the device is a mirror that reflects the child's existing personality, not a force that creates new ones. A second counterargument claims that technology can indeed rewrite habits entirely, but that this power is limited by the child's broader environment. Parents, schools, and community activities still set the main rules for how a child spends time. Even if a child spends hours on a screen, a parent who limits bedtime, encourages outdoor play, and talks about feelings can steer the child's development in a different direction. This view suggests that digital influence is strong, but not absolute. Real-world applications of these ideas are already visible. In education, many schools use tablets to let students explore science simulations. A student can change variables in a virtual lab and see immediate results, something that would be costly or dangerous in a real lab. In health, doctors use apps that remind teenagers to take medication, track sleep, or practice mindfulness. These tools show how digital nurture can be guided toward positive outcomes. In the world of work, the teamwork skills learned in online games are being recognized by employers. A study by the University of California found that players of multiplayer games often display higher levels of coordination, quick decision-making, and the ability to share information under pressure. Companies now run gamified training sessions that mimic these environments, hoping to transfer those skills to real projects. Social feeds also have a clear impact on self-image. A teenager scrolling through Instagram may compare their own photos to the polished images of peers and influencers. Research from the University of Pennsylvania shows that higher use of image-focused platforms can increase feelings of inadequacy and lower self-esteem. On the other hand, platforms that promote supportive communities, such as those focused on hobbies or learning, can boost confidence and provide a sense of belonging. To make these ideas more vivid, two analogies help. First, think of a garden. The soil, sunlight, and water are the natural conditions that allow a plant to grow. Technology is like a set of garden lights and sprinklers that can be turned on or off. The lights can help the plant grow faster, but they cannot make a seed that is not suited for the climate become a thriving rose. Similarly, a child's genetic makeup and early experiences set limits, and technology can nurture within those limits or push a little farther, but it cannot change the seed itself. Second, imagine a river that flows through a city. The river's path is set by the landscape, but the city can build dams, bridges, and canals that direct the water to new places. Digital tools act like those structures. They can channel attention, emotions, and learning toward certain directions, but the water still follows the basic flow of the river. The child's mind is the river. Technology builds the channels. Historical anecdotes show how new media have always reshaped nurture. The first social network, 6degrees.com, launched in 1997, allowed people to list friends and connect across distances. At the time, many thought it was just a novelty, but it introduced the idea that relationships could be managed online. Within a few years, Friendster and MySpace added photo sharing and music playlists, turning the internet into a place where identity could be displayed and tested. These early platforms set the stage for today's massive networks, showing that the digital environment has been influencing social habits for more than 2 decades. Another early study on screen time came in the 1970s, when researchers at the University of Illinois measured how much television children watched and how it related to reading ability. The study found that children who spent more than 3 hours a day in front of the TV scored lower on reading tests. Although the medium was different, the findings sparked a long line of research that now includes tablets, smartphones, and gaming consoles. The pattern that more screen time can affect learning has persisted, but the content and interactivity have changed dramatically. These anecdotes link directly to the culture and interactionist sections of the larger discussion. Culture shapes what kinds of apps become popular, and interactionist ideas explain how people negotiate meaning through digital symbols. For example, the rise of memes as a cultural shorthand shows how a simple image can carry complex social commentary. The way a child learns to use memes in conversation reflects both the cultural trend and the interactive process of making sense of symbols online. Quotes from primary sources add depth to the picture. Sherry Turkle, speaking in a 2015 interview, said, "We are not just using technology. We are letting it shape how we think about ourselves and each other." Nicholas Carr, in the same essay that sparked debate, wrote, "The net encourages us to skim, to jump, to move quickly from one idea to the next, without staying long enough to think deeply." Both statements underline the twin forces of opportunity and risk that digital nurture brings. The child learning from a tablet can also be seen through the lens of a simple analogy. A child with a flashlight in a dark room. The flashlight, the tablet, can illuminate hidden corners, reveal new shapes, and help the child navigate. Yet the child still needs to learn how to turn the flashlight on, where to point it, and when to put it down. The device offers light, but the child's curiosity and willingness to explore decide what is discovered. In practice, the teamwork skill from online gaming can be illustrated by a popular game called Fortnite. In that game, a squad of 4 players must gather resources, build defenses, and coordinate attacks. Success depends on clear communication, quick role changes, and shared goals. Researchers have observed that players often develop a sense of team mind, where they anticipate each other's moves without speaking. Those same skills can translate to school projects, where students must divide tasks, give feedback, and adjust plans on the fly. Another concrete example is the effect of social feeds on self-image in the context of culture. A teenager may spend an hour each day watching short videos that showcase dance moves, fashion tips, or comedy sketches. The algorithm shows more of what the teenager watches, reinforcing certain styles and attitudes. If the teenager receives many likes on a video where they dress in a particular way, they may start to adopt that style more often, feeling validated by the digital crowd. Conversely, if the feed constantly shows idealized bodies and perfect lives, the teenager may feel pressure to conform, leading to anxiety or body image concerns. Both examples show how digital environments can shape habits, values, and skills. They also illustrate the two counterarguments. In the gaming example, a child who already enjoys problem solving may find the game amplifies that trait, supporting the view that technology mirrors existing tendencies. In the TikTok example, a child who was previously indifferent to fashion may develop a new habit of curating their appearance, suggesting that technology can rewrite habits. Modern interpretations of the nature versus nurture debate now include the term the gene-environment interaction. This phrase means that genes and experiences work together, each influencing the other. Some scientists use brain imaging studies to show that children who spend a lot of time on fast-changing digital media have different patterns of activity in regions linked to attention and reward. Others caution that such changes are not permanent and can be reshaped by later experiences, such as reading books or engaging in outdoor play. The conversation also reaches into policy. Some schools have created digital wellness programs that teach students how to set screen time limits, recognize online pressure, and balance virtual and real-world activities. Governments in several countries have introduced guidelines for the amount of screen time allowed for children under a certain age, echoing the early research on television. These policies reflect the belief that nurture can be guided, even when the environment is largely digital. Looking ahead, the future of digital nurture may involve more immersive technologies like virtual reality, VR. Imagine a child wearing a headset that places them inside a simulated rainforest, where they can touch virtual leaves, hear birds, and learn about ecosystems. Such experiences could deepen learning far beyond a flat screen. Yet the same technology could also isolate the child from real peers, if not balanced with face-to-face interaction. The potential for both enrichment and over-reliance mirrors the dual nature of all tools. In sum, the picture of a child learning from a tablet opens a wide window onto the new nurture landscape. Thinkers like Turkle and Carr have highlighted how technology reshapes identity and attention. Real-world examples from online gaming and social feeds show how digital tools can build teamwork and affect self-image. Counterarguments. The discussion now turns to the ethical side of nature and nurture. It asks what people owe each other when they think about genes and environment. The coach analogy helps to see the stakes. A coach can see a player's natural talent, but the coach also decides how many drills, how many minutes of practice, and what encouragement to give. The coach's choices shape the player's future as much as the player's body does. In the same way, societies make choices about education, health, and work that mix nature and nurture. Those choices raise moral questions about fairness, responsibility, and the kind of world that is wanted. Peter Singer often frames moral duty in terms of preventing suffering. He writes, "If we can prevent something bad from happening without sacrificing anything of comparable moral importance, we ought to do it." Applied to nature-nurture, the quote pushes the idea that if a society can reduce the harm that comes from genetic disadvantage, it should act, as long as the cost is not too high. Judith Jarvis Thomson, famous for her violinist thought experiment, reminds that rights are not absolute. She says, "The right to life does not entail the right to be sustained." In the nature-nurture debate, this suggests that having a certain genetic make-up does not guarantee a right to the same outcomes if the environment does not support the person. One everyday example is how schools handle gifted programs. Some districts use test scores to place children in advanced classes. The test scores often reflect both innate ability and the support a child receives at home. If a child comes from a family that can afford tutors, the child's score may be higher and the child gets more challenging work. The policy then rewards the combination of nature and nurture, but it can also lock out children whose families cannot provide extra help. The moral question becomes, is it fair to give more resources to those who already have an advantage? Should schools try to level the playing field by offering extra support to all, or should they let natural talent decide who moves ahead? A second everyday example is workplace accommodations for employees with learning differences. A company might offer flexible hours, assistive software, or quiet workspaces for people with dyslexia or ADHD. Those accommodations recognize that the environment can be changed to help people succeed despite genetic or neurological differences. The ethical issue is whether the company has a duty to make these changes, and whether offering them creates a sense of entitlement or fairness. The answer depends on how much the society values equality of opportunity versus equality of outcome. Two strong counterarguments appear in public debates. The first says that genetics should dictate opportunity. Proponents argue that because genes set a ceiling on what a person can achieve, society should not waste resources trying to raise someone beyond that ceiling. They claim that giving extra help to someone with a low genetic ceiling is inefficient and unfair to those with higher ceilings. This view often cites studies that link IQ scores to job performance, and it calls for policies that match people to roles that fit their innate abilities. The second counterargument flips the blame onto the environment alone. It claims that any failure to succeed is the result of poor schooling, bad parenting, or a hostile community. From this angle, genetics play no real role, and the solution is to improve schools, raise incomes, and eliminate discrimination. Advocates of this view point to stories of people who rose from poverty to great success after receiving a scholarship or a mentor. They argue that if the environment is fixed, no one will be left behind, and genetics become irrelevant. Both counterarguments miss the middle ground that most philosophers and scientists accept. Genes give a range of possibilities, but the environment moves a person toward one point in that range. The coach analogy shows that a good coach does not ignore a player's natural skill, nor does the coach force the player to train beyond safe limits. The coach finds a balance that respects the player's body while still offering growth. History offers vivid anecdotes that illustrate how societies have taken extreme positions. In the early 20th century, the eugenics movement in the United States and Europe pushed the idea that genetics should decide who gets to reproduce and who should receive public aid. Laws were passed that forced sterilization on people labeled unfit. The movement claimed that removing the bad genes would improve society. The result was a huge violation of human rights, and the scientific basis was later discredited. This dark chapter shows the danger of letting genetics alone dictate policy. A contrasting story comes from the civil rights push for equal education in the 1950s and 1960s. When the Supreme Court ruled in Brown v. Board of Education, it declared that separate schools are inherently unequal. The decision recognized that the environment, segregated, underfunded schools, kept black children from reaching their potential, even if they had strong natural abilities. The civil rights activists argued that society must change the environment to give every child a fair chance. Their work led to laws that required integration and more equitable funding, showing how changing nurture can open doors that genetics alone could not. These anecdotes link back to earlier sections on policy and culture. The policy part explained how governments set rules that shape the environment, while the culture part described how shared beliefs about talent and effort influence those rules. The ethical part now asks which policies are just, and how cultural attitudes should shift. One way to think about responsibility is to ask who is at fault when a child does poorly in school. If the child's parents have a learning disability, the child may inherit that difficulty. If the school lacks trained teachers, the child's environment is lacking. Holding only one side responsible ignores the interaction. A balanced view says that families, schools, and the state all share responsibility. This view matches Singer's idea of preventing harm without causing comparable loss. It also respects Thompson's point that rights come with duties. A child's right to education brings a duty on schools to provide suitable support. Another angle is the concept of full moral luck. Moral luck means that people can be praised or blamed for things that depend on factors beyond their control, like genetics. If a student with a natural aptitude fails because of a noisy classroom, is the student to blame? Most people would say no. The ethical implication is that society should not judge people harshly for outcomes that stem from genetic luck. Instead, society should aim to reduce the impact of that luck by improving the environment. In practice, policy can try to balance these concerns. Some school districts use a dual-track system for gifted programs. One track selects students based on test scores, while another track offers enrichment to students who show promise but lack resources. The dual track tries to honor natural ability while also correcting for unequal nurture. Critics say the system still favors those with better home support, but supporters argue it is a step toward fairness. In the workplace, companies may adopt universal design principles. Instead of creating special accommodations for a few, they design tools that help everyone. For example, software that offers multiple ways to input data, voice, typing, or touch, helps people with different abilities. This approach reduces the stigma of special treatment and acknowledges that the environment can be built to fit many bodies and minds. It also reflects the ethical stance that society should not just patch problems after they appear, but should create inclusive spaces from the start. A further illustration comes from public health. Consider a program that offers free nutrition counseling to pregnant women in low-income neighborhoods. The program assumes that both genetics, the health of the mother and baby, and environment, access to healthy food, matter. By improving diet, the program hopes to reduce birth complications that are linked to both genetic risk and poor nutrition. The ethical question is whether the state should fund such programs. Singer's principle would say yes, because the program prevents suffering at a modest cost. Opponents might claim that individuals should take responsibility for their own health. The debate mirrors the earlier counterarguments about genetics versus environment. The discussion also touches on the idea of well-deservedness. Some people feel that those who succeed deserve their success because they have the right genes. Others feel that success is largely due to hard work and supportive surroundings. The truth lies between. A person with a strong genetic predisposition for musical talent still needs a teacher, an instrument, and practice time. Conversely, a person with modest talent can become a competent musician through intense training. The ethical implication is that society should recognize both the role of natural gifts and the importance of providing opportunities for growth. Quotes from primary sources help to keep the conversation grounded. In his 1975 book, Animal Liberation, Peter Singer writes, "Though the question is not whether we have a right to life, but whether we have a right to a life that is worth living." Though the book deals with animal rights, the line can be applied to human beings with genetic disadvantages. If a child is born with a condition that makes daily life painful, society has a duty to ease that pain, not to abandon the child because the condition is natural. Judith Jarvis Thomson, in her 1971 essay, A Defense of Abortion, says, "The right to life does not entail the right to use another's body against his will. This underscores that rights come with limits, and that society can set limits on how far natural traits dictate outcomes." The coach analogy can be extended to a team sport like soccer. A player may have fast legs, but without proper drills, the player may not learn how to pass the ball. If the coach gives too much training, the player may get injured. The coach must watch the player's limits and push just enough. In a society, lawmakers act as coaches. They must look at data about genetic risks, like higher rates of heart disease in certain groups, and decide how much public health effort to invest. Too little effort leaves people vulnerable. Too much effort might be seen as overreach. Another analogy uses gardening. A seed carries the genetic code for a flower. Some seeds are more likely to grow tall, some are dwarf. Yet the gardener controls soil, water, sunlight, and pests. A seed that would normally grow short can become a healthy plant if the gardener provides rich soil and plenty of water. Conversely, a tall seed can wither if the soil is poor. The gardener's choices shape the final outcome, just as policies shape how genetic potentials are realized. Returning to the two everyday examples, the gifted program shows how a policy can unintentionally widen gaps. If a school only looks at test scores, children from wealthy families may dominate the program, while talented children from poorer homes are missed. Some districts have tried to add holistic review that looks at teacher recommendations, creativity, and perseverance. The change reflects an ethical move to see beyond raw scores, acknowledging that nurture can hide or reveal talent. In the workplace, the case of an employee with dyslexia who asks for a screen reader shows how a small change can unlock productivity. The employee can then contribute ideas that improve the whole team. If the employer refuses, the employee may quit, and the company loses a valuable perspective. The ethical choice is to see the accommodation as an investment in human capital, not as a special favor. The counterargument that genetics should dictate opportunity often cites the idea of meritocracy. It says that people who have the best genes will naturally rise to the top, and that helping those with weaker genes is unfair. This view ignores the fact that merit itself is shaped by opportunities. A child who can read early because of a supportive home will appear more meritorious than a child who cannot, even if both have similar potential. The meritocracy claim therefore rests on an incomplete picture of how abilities develop. The opposite counterargument blames the environment alone. It says that any failure is because society did not provide enough schools, enough mentors, enough jobs. While this view highlights the power of nurture, it can also erase personal agency. Not every person who receives a good education becomes successful. Some still struggle due to health issues, mental illness, or personal choices. The balanced view holds that both nature and nurture matter, and that ethical policy must address both. Historical anecdotes help to see the consequences of extreme positions. The eugenics movement, championed by figures like Francis Galton, pushed for compulsory sterilization laws. In the United States, over 60,000 people were sterilized under state laws before the practice was halted. The movement's moral logic was that society should prevent defective genes from spreading. The tragedy shows how an overemphasis on genetics can lead to cruelty and loss of freedom. In contrast, the civil rights era fought against policies that kept black children in underfunded schools. The activists argued that the environment of segregation denied children the chance to use their natural gifts. The Supreme Court, the future of the nature versus nurture debate, looks like a garden that uses both old soil and new tools. Imagine a gardener who places tiny sensors in the ground. The sensors tell the gardener when the soil is dry, when the sun is too strong, and when a plant needs extra food. In the same way, new science puts tiny guides into living cells and into learning programs. These guides help people see how genes and experience work together. One of the most visible new tools is CRISPR. CRISPR is a pair of molecular scissors that can cut DNA at a chosen spot. The tool was first shown to work in a lab by Jennifer Doudna and her team in 2012. Doudna later wrote, "We have only begun to understand the power of editing the code of life." The quote reminds viewers that the power is still early. CRISPR lets scientists change a single gene that may cause a disease. In a recent trial, doctors used CRISPR to edit the gene that makes sickle cell anemia. The trial showed that a child's blood cells began to make healthy hemoglobin. This example shows how a single genetic change can improve health, a clear link to the nature side of the debate. Another new tool is AI-driven learning. Daniel Kahneman, a psychologist who won a Nobel Prize, has said, "The confidence we have in our beliefs is not a reliable guide to their truth." Kahneman's warning fits well with the rise of adaptive learning apps. These apps watch how a student solves a math problem. If the student makes a mistake, the app offers a simpler example. If the student solves a problem quickly, the app moves to a harder one. In schools across the world, such apps are being used to give each child a learning path that fits their pace. The apps show how experience, or nurture, can be shaped by data. The garden analogy helps explain the balance. The gardener's soil is like a person's genes. The sensors are like AI that tell the gardener when to water. The gardener still decides when to prune. In the same way, scientists can edit a gene, but they still need to decide how to use that knowledge in society. The story of the first gene editing experiment adds a historical flavor. In 1972, a scientist named Paul Berg created the first recombinant DNA molecule. He glued together DNA from two different viruses. The world reacted with both excitement and fear. Some people worried that mixing DNA could create dangerous new life. The concern led to the Asilomar Conference, where scientists gathered to set rules for safe work. The conference showed that even early on, the field respected ethical limits. That lesson is still useful as CRISPR becomes more powerful. A second historical anecdote comes from the rise of massive open online courses, or MOOC. In 2012, 2 universities offered free courses to anyone with internet access. The courses attracted millions of learners. Some educators feared that free courses would replace teachers. Others saw the chance to reach people who never could attend a campus. The MOOC movement showed that new technology can change how knowledge spreads, but it also reminded people that human connection still matters. The MOOC story ties back to the nurture side, showing how experience can be shared on a large scale. Real-world applications of these tools are already appearing. In the gene editing trial for sickle cell disease, doctors measured the level of edited cells in the patient's blood each month. The numbers rose steadily, and the child's pain attacks dropped. The trial gives hope that a single gene change can alter a life. In another case, an adaptive learning app called MathPath was used in a middle school. Teachers reported that students who used the app improved their test scores by 10 points on average. The app's data also showed which concepts caused the most trouble, allowing teachers to focus their lessons. These examples illustrate 2 ways the future may unfold. One path leans on technology to shape nature directly. The other path leans on technology to shape experience. Both paths need careful thought. One counterargument warns that technology may overstep ethical lines. Critics point to the possibility of war designer babies. If parents could choose eye color, height, or even personality traits, the line between healthcare and personal preference could blur. Some ethicists argue that allowing such choices could increase social inequality. They fear a world where only wealthy families can afford to give their children genetic advantages. The fear is not just about the science. It is about how society treats those who are different. A second counterargument says that human tradition still matters most. Even with the best sensors, a gardener still needs to feel the soil, see the sunrise, and listen to the wind. In education, a teacher's smile, a story shared at the lunch table, and a community's values shape a child's mind in ways that data cannot capture. Some scholars argue that over-reliance on AI could reduce empathy and make learning feel cold. They point to cultures that have kept oral traditions alive for centuries, showing that nurture can thrive without high-tech. Modern interpretations try to blend these views. Some philosophers suggest that nature and nurture are like 2 threads in a rope. The rope is stronger when the threads are woven tightly together. Others propose a feedback loop model. In this model, a gene may set a range of possible outcomes, but the environment pushes the outcome toward one end of that range. The loop keeps turning as the person grows, learns, and even changes their own biology through habits. The garden analogy can be extended to illustrate the feedback loop. The soil gives the plant its basic nutrients, but the plant also changes the soil by dropping leaves that decompose. The sensors tell the gardener when the plant is thirsty, and the gardener waters it. In the same way, a child's brain may have a genetic tendency toward anxiety, but supportive teachers and friends can help the child develop coping skills. Those skills can even change brain chemistry, showing how nurture can affect nature. To bring the ideas home, 2 everyday examples are useful. First, consider a family where a child inherits a gene that raises the risk of high cholesterol. The family learns about a new CRISPR trial that can edit the gene in early childhood. The parents face a choice: wait for the trial to finish, or rely on diet and exercise. The decision involves both the nature side, the gene, and the nurture side, lifestyle. Second, picture a high school that adopts an AI-driven reading program. The program adjusts each student's reading level each day. One student, who struggled with reading at home, suddenly finds the right level and begins to enjoy books. The program's success shows how technology can tailor nurture to each learner's needs. The future also holds tools that combine both approaches. Researchers are working on epigenetic editing. Epigenetics is the study of how chemical tags on DNA turn genes on or off. By adding or removing these tags, scientists can influence how a gene behaves without changing the DNA sequence itself. This method respects the gene's original code while still allowing change. It is a middle ground between editing the script and directing the actors. Another emerging field is more personalized education. Using data from wearable devices, schools could monitor a student's stress level, sleep patterns, and attention span. The data would feed into an AI that suggests when the student should study, when to take a break, and what type of activity would help them retain information. The system would not replace teachers, but would give them a clearer picture of each student's needs. Both fields raise new ethical questions. Who owns the data from a student's wearable? How can privacy be protected? What happens if a school decides to use gene editing to improve athletic performance in its students? These questions echo the earlier concerns about designer babies and the need for public discussion. Linking back to earlier parts of the video, the discussion began with the classic debate of nature versus nurture. The first section traced the idea back to ancient philosophers who asked whether a person's character was set at birth or shaped by experience. The next part examined early experiments in psychology that showed how environment could change behavior, such as the famous rat maze studies. The third section explored modern genetics, highlighting the discovery of DNA and the rise of twin studies. Those sections built a picture of a long conversation that has moved from simple questions to complex science. Now, the future directions build on that history. The garden image connects the old idea of soil, genes, with the new idea of smart sensors, data. The quotes from Doudna and Kahneman remind viewers that both science and psychology still warn against overconfidence. The historical anecdotes of the first recombinant DNA work and the launch of MOOCs show how each new tool sparked both excitement and caution. The counter-arguments keep the balance, reminding that technology is not free of risk and that human tradition still holds value. In the end, the story of nature versus nurture is not a battle but a partnership. The partnership is like a gardener who respects the land, uses tools wisely, and listens to the weather. As CRISPR, AI, and new learning platforms grow, the gardener will need to ask, how much should the tools change the garden? And how much should the garden guide the tools? The answer will shape not just science, but everyday life for the next generation. The takeaway for everyday viewers is simple. First, stay curious about new science, but also stay aware of the moral choices it brings. Second, support education that blends technology with human care. Third, remember that each person carries both a genetic code and a life story, and both can be nurtured. By seeing the future as a garden with smart sensors, viewers can picture a world where nature and nurture grow together, guided by thoughtful hands.